For the afternoon is by Cyril Demarche, and he has beautifully written the title on the board.
Thank you, and I want to thank the organizers for the invitation. So I will talk about homogeneous spaces and their structure and some applications to local global principles. There is a connection with the talk by David Harari on Monday, where he already mentioned some results about homogeneous spaces, and especially over function fields. So here we will be in the setting of number fields. And in the talk by David Harari, the strategy was to use abelian Galois cohomology and arithmetic duality theorems. Here we will have a non-abelian approach to this problem. And well, let me start with a precise introduction. So in all the whole talk, k, little k will be a number field. G will be a linear connected algebraic group. And X will be a homogeneous space over K, a homogeneous space of G. And so the variety G, X, well, since algebraic group over K bar are rational varieties, X is geometrically unirational. So we can think about Colliot-Helen conjectures, about rational points for rationally connected varieties. And if you apply this conjecture to, say, a smooth compactification of X, then we expect, well, at least it is a question. What can we say about the relation between local and global points? So, is the set of rational points dense? So maybe I will just state it as follows. So if Y is a smooth compactification of X, do we have that the closure of rational points on Y in the adelic points of Y, is this closure equal to the Brauer-Manin set? Okay, this is the main question we are interested in. So this question is still open in this setting of homogeneous spaces of algebraic groups. So still open, but some cases are known. So I could start with smooth quadrics, because this is the classical Hasse-Minkowski theorem. So maybe in the history, this is one of the first examples, I think. So here you don't need the Brauer-Manin obstruction. And more generally, if you're interested in, as in the talk by David Harari, if you're interested in a principal homogeneous space, so if you assume the stabilizers are trivial, then the conjecture, well, the answer is yes to this question. And the case of semi-simple, simply connected groups has a long story, but I can give a few names here. Knesser, Harder, Chernouzov, at least. And for the case of tori and the general case of linear algebraic groups, I can mention Voskresensky and Sansuk. And the third example is, well, the most general example is the case when stabilizers of geometric points on X are connected. So if geometric stabilizers are connected, then the answer is yes, and this is a result by Borovoy that was already mentioned in this conference. And essentially, this is what is known, or what was known before some recent work by Olivier Wittenberg and Jonathan Harpaz. And I will try to explain ideas and about how to try to get rid of the connectedness assumption in the example by Borovoy. So the first motivation to study this question is the general conjecture by Colliot-Helen. And maybe another motivation to study this problem on those special varieties is the following. So if you believe in the conjecture for X equals SLN modulo a constant finite group, an abstract finite group, then the conjecture implies, so if X, or Y with my notations, if Y is dense in the adelic set, then H is a Galois group of a K, and much more. So we have a positive answer. So yes, H is a Galois group of a little k. And we have some weak approximation property for the Galois extension. So we can prescribe some local conditions outside the given finite number of places. So this is a strong version of the inverse Galois problem, so which is also an open problem. So this is another motivation maybe to study this problem. So the questions now are can we remove the connectedness assumption? And what is the precise connection between this very special case and the general conjecture by, the general conjecture for homogeneous spaces? So the first theorem I want to mention, which will be the one I will try to prove in this lecture. So before, I should have said it before. So all of this is joint work with Giancarlo Lucchini-Arteche in Santiago. And the first theorem is the following. So if so what I will call here so let me give a name at this for this property here. star. So if star is true for homogeneous spaces of SLN with finite stabilizers, then it's true for all homogeneous spaces. So in some sense, this particular example is really the crucial case. So this is not so surprising because if you think of Brauer result, okay, we know how to deal with the connected case. So there is some finite component to deal with, and okay, there is this finite group somewhere, and so this is not very surprising, but I think the proof is not as easy as one could think first. And I want now to mention a second result, which is due to Harpaz and Wittenberg. In 2018, I think. And they proved that so this property here, or almost, well, so they prove a very nice result for the analogous property for 0 cycles of degree 1. So star holds, so for homogeneous spaces of SLN, well, in fact, you can generalize this a little, of SLN with finite stabilizers, if you replace here and here, I will give the precise version afterward, but if you replace here and here rational points by 0 cycle of degree 1. So if rational points are replaced by 0 cycles of degree 1. And if you put together these two results, of course you have to modify a little this statement to replace also 0 cycles of degree 1, rational points by 0 cycles of degree 1. If you put those together, you get the following consequence. No, it's not this one. So you can get as a corollary. So it is in the paper by Harpaz and Wittenberg. You get the following corollary. If you put the two theorems together, you get that star for 0 cycles of degree 1 holds for arbitrary homogeneous spaces of linear algebraic groups. Or smooth compactification of such varieties. Which is a really nice result. I mean, because it was essentially open even for 0 cycles of degree 1 outside the case of connected stabilizers. It was almost nothing was known. So this is a nice progress by Harpaz and Wittenberg. And unfortunately, this does not give, it doesn't have nice, Galois interpretation as we could expect from this rational point version here. But anyway, you know that there is also a conjecture by Colliot-Helen for 0 cycles of degree 1 for any smooth projective variety. So this is a new example for this conjecture.
Cyril?
Yes?
Have you example of homogeneous spaces under SLN which has a 0 cycle of degree 1 and no rational?
There are some examples, I think, in the PhD thesis of Mathieu Florence. I think I don't remember the example, but I think so. But maybe Parimala knows also something about this.
Finite stabilizer. Finite stabilizer.
Yeah, with finite stabilizer.
That is Matthew.
Yes, yeah, I think so.
With connected stabilizer, it's still open.
Yes, probably yes. So, yeah. Yes, Parimala has examples with connected stabilizer, and Mathieu Florence has examples with finite stabilizers. So before proceeding to the ideas of proof, I want to give a precise statement of the conjectures for 0 cycles of degree 1, because I think we didn't see this conjecture for 0 cycles, so I want to state it now here. Star for 0 cycles of degree 1. So there are variants of this conjecture, but the one I can write now is the following. Says, so you're interested in the Chow group of 0 cycles for the smooth compactification of the homogeneous space. You map it to the product of the local analogs of this group, and you have a natural extension of the Brauer-Manin pairing to 0 cycles to 0 cycles. So you get a map to the dual of the Brauer group of Y, and essentially the conjecture says that this sequence is exact. I think in this case we don't need completions, right? You agree? Yeah. Okay. In this case, we don't need completion. So in the special case here, this is really the statement. Well, one of the versions of the statement is an exact sequence. So you can you can detect if local 0 cycles are global by the Brauer-Manin obstruction. Okay. Okay, so now I will explain how to. So I won't give details about the proof by Harpaz and Wittenberg. It is really a very nice argument with combining descent theory and the vibration results, vibration method, and also there is a reduction to P groups, to the CELO subgroups of the given finite subgroup. But I will focus on the reduction statement. And I will do it in 2 steps. The first step will be the case when we have a rational point on the homogeneous space, because things are easier and everything is defined over the ground field, and you can make this some natural dévissage on the group and on the stabilizer to simplify the structure of X. So the section 2 is when when we know a priori that we have a rational point on X. So this particular case, so we are not interested in the Hasse principle anymore, only in weak approximation, right? This particular case. The reduction for this case was proven by Giancarlo in 2018, 17, I think, 17, yes. Sorry. And the idea is as follows. So in this case, of course, you can fix a point. So X is isomorphic over K to a quotient G mod H, okay? Where H is an algebraic subgroup of G over K. And the idea is to, because I didn't mention it, but in fact, the statement of theorem 1 is a bit more precise. In fact, for any X, we construct an essentially explicit homogeneous space X prime of SLN with finite stabilizer, which is sufficient to test the conjecture for the initial X. And the idea is to construct a new homogeneous space. So construct X prime, which will be something like SLN over some finite group H prime with H prime finite, so that weak approximation with Brauer-Manin obstruction for X is equivalent to the same result for X prime. Okay, so star for X is equivalent to star for X prime. And how do you do this? I will state it in a maybe too complicated way, but it is on purpose to make things easier in the next part. So the idea is the following. First, in the case of when rational points exist on homogeneous spaces are essentially equivalent to the data of an algebraic subgroup of a given algebraic group. Okay? So I can say it like this. So if you consider pointed homogeneous spaces, and what I mean by this, more precisely, if you give an algebraic group a homogeneous space and a rational point on it, this data is the same as the data of, say, a closed immersion of an algebraic subgroup into an algebraic group. So embedding of linear algebraic groups, in the sense that here you consider the data of G, H, and an inclusion of an closed immersion of H into G. These two things are equivalent. Of course, here you attach to this data the stabilizer. So in this direction, H is just a stabilizer of the point, right, inside G. And the other direction, you just take the quotient. Okay? Equipped with the canonical point coming with this structure, right? Okay, so this is just a fancy way to say that it is sufficient to deal with this morphism of algebraic group from H to G, and we will simplify, and this is functorial. Okay, in some sense. So we will simplify the structure of H and G in order to simplify the structure of X. This is the idea. And the second step, the second ingredient in the proof of the case of homogeneous space with a rational point is the fact that the very basic fact that any linear algebraic group H over K embeds into some SLN for some big N. Essentially, this enables you to produce new homogeneous spaces with the same stabilizer and to make the reduction. So the third step, putting these two things together, is just to make a dévissage, which I will explain in the general case afterwards, on H and G. Okay? Using the known results about the structure of algebraic groups over a field. Okay? So this is the main idea, which is very natural. But I want to focus on the Hasse principle problem. So the case when you don't know a priori that X has a rational point. So general case. And the idea is to try to generalize this equivalence here and this basic fact to similar statements in the case of homogeneous space of without rational points. Okay? So we do not assume that X has a rational point. Sorry. So we need replacement for properties 1 and 2. Mentioned above. And to do this, we will use non-abelian cohomology. Cohomology. Or in fact, I don't think I will write any cohomology group or set, but the idea is from non-abelian cohomology. And more precisely, non-abelian H2. So I will have to give a few definitions before stating the analogs of property 1 and property 2. So the first definition is a definition of a gerb. So in this particular setting here, so a gerb over the field K is just, so this is a stack over the small étale site of K. So I will give a concrete definition of this word right after the definition here. A stack in groupoids. So on the small étale site of spec K, which has nice properties. So a stack, say M, for instance, And the nice properties will be that M is locally non-empty and M is locally connected. So what does it mean, locally non-empty? Concretely, it means that you can find a finite extension, and you can assume that it is a finite field extension, such that M has capital K rational points. And any points, so for all finite extension and for any points M and N prime in capital K, the points M and M prime are locally isomorphic, which means that you can find a bigger finite extension, L over K, finite, and an isomorphism between M and M prime in the category M of L. So now I will explain what the word stack here means. Recall that a stack M is essentially the following data. So for any, so you were given some categories, groupoids even here. So groupoids M of capital K for any étale algebra. So for any étale algebra of a little k, you consider a category depending on capital K, étale algebra. Together with base change or extension functors. So there are extension or base change functors from Mk to Ml for any K embedded for any algebra L over the algebra K. Okay, satisfying some compatibilities. So you have to think compatibilities. So this is what is called essentially a fibered category. Okay, a category for each étale algebra of a K. And to have a stack, you need to you need to have a descent property. So how do I write it? Yeah. So descent data. In this setting, you can consider, for instance, element in M of capital K, and you would like to know, do they come from M of little k? And this can be done looking at section over capital K, tensor capital K over little k, as in classical, say, FPPF descent or Galois descent. So descent data are effective for object of in these categories and also for morphisms. This is essentially what a stack will be in this talk, and morphisms. Okay. So why do we need such a strange thing here? The idea is that this object, a gerb, is a very natural way to to encode a descent theory, say, without cocycles. If you consider Galois descent, usually you twist something over k-bar by some Galois cocycle, and it can be quite tedious to check everything and to check that is functorial, that it does not depend, does it depend or not on the, only on the cocycle or on the chronology class and so on. Here you can do it more geometrically and more canonically. So this is the object I want to consider. And now I will explain the application to our problem. So here I am over a number field. So there are no problems. Everything extends, even the reduction theorem in some sense. The reduction theorem I will mention extend to any perfect field if you consider only, say, smooth algebraic groups. Everything works over a perfect field. Otherwise, you will have to consider analogs of such jobs but for the FPPF chronology. Here, this is an étal or Galois gerb. So maybe I have to write an example now of a gerb. And the one you have to have in mind is the following. So if you consider, say, an algebraic group over K, over little k, the category, or the fibered category of torsors under H, which is given by, so I have to define it for any little k étal algebra capital K. And the category is just the category of torsors of a spec K under the group H extended to capital K, so the category of torsors with natural morphisms and so on, is a gerb. Okay? So you can check that you have, of course, classical descent theory works here, and it is locally non-empty. Of course, you have the trivial torsor over the little k, and two torsors are isomorphic locally. This is also a classical property. So this is what you have when I will write down a gerb. You have to think about this example, and note that for given any gerb, say M over little k, and a point, an object in the category M of little k, you get an isomorphism. I didn't explain what an equivalence. I didn't explain what a morphism of gerb is, but you can make the definition. From this to a gerb of torsors under some algebraic group, or at least some sheaf in groups, which is a sheaf of automorphism of the given object. If you're given an object, then the group of automorphism is a sheaf because of this descent assumption for morphisms. So this is the same thing as this one, except that H is not necessarily representable in general, but it's not important. So you can check that the map sending a section M prime to the sheaf of isomorphism from M to M prime is a torsor under the automorphism of M. This is you also use the fact that two objects are locally isomorphic. Okay, so in some sense, a gerb is just something that is locally isomorphic to this example. Really in the same spirit as a torsor is something that is locally isomorphic to the group H with the action on itself by translation. Okay? Okay, so this is what I mean by by a gerb. So of course it was introduced by Giraud in a much more general setting. But here we will only need the Galois case. And remark, gerbs locally isomorphic to a gerb of torsor and of torsors under H are classified, are essentially classified by the non-abelian H2 that I mentioned earlier. Okay? This is why, in fact, now we are dealing with non-abelian H2, but I think I won't need this notation. And now we can generalize the statements 1 and 2 about the structure of homogeneous spaces as follows. So first, 1 becomes an equivalence of category. An equivalence of categories between the category of, say, homogeneous spaces, and I do not require the existence of a rational point, and some categories, say, of what we can call homogeneous gerbs, and it replaces the embeddings of algebraic groups. And the equivalence of category is given as follows. So here you consider an algebraic group and a homogeneous space of it, okay? And you can associate to it a gerb. So the group, well, yeah, a gerb mx associated to x. So this will be a gerb, right? Together with a kind of embedding to what replaces the group G is the trivial gerb of torsors under G. And this is a natural generalization of the embedding of H into G that we had before, except that here, of course, if X has no rational point, in general, the stabilizer of a geometric point is not defined over K. The thing that is defined over K is this stuff here, which is locally isomorphic to the gerb of torsors under H, under the geometric stabilizer. So this is an object defined over K that captures the geometric stabilizers over extensions of K. Maybe I can write down what mx is, because it is really easy to write. So what is mx of a given an algebra K? Okay, so this is one. I will explain in point 2 right after. So given an étal algebra as before, what is mx of K? This is just the category of G torsors, GK torsors of a spec of capital K. So it makes sense, except that you consider torsors equipped with a morphism to the given homogeneous space under G. Okay, this is the natural map, the structure map of the homogeneous space extended to capital K. And you consider morphism alpha that is equivariant. This is a torsor, this is the homogeneous space of G. You consider morphisms that are G equivariant. Okay? This is a category with a natural notion of morphisms. Okay? Is there a question?
This is a static quotient by G or divided by G?
Yes, I think so. Yes. It's the same. Yes. But and in some sense, Well, it is a natural obstruction for x to have a rational point. The first obstruction, in some sense, to have a rational point is that x is dominated by a torsor under G, because if it has a rational point, it is dominated by G itself. So the first step you ask, is it dominated by a torsor? And then you are reduced to a question of H1. Is this torsor trivial? Okay? So this is the germ associated to the homogeneous space. And you also have a construction in the opposite direction, similar to taking the quotient of G by a subgroup, but here you have to work a little more to construct the associated homogeneous space. Okay? So this is the replacement for statement 1. And we will, so instead of working geometrically with X, we will make some dévissage both on G and on the germ M associated to X. Okay? And the replacement for statement 2, which was any linear algebraic groups can be embedded into some SLN, is the analog. So any so you have to define a replacement for algebraic for linear group. So I will write linear germ M. It just means that if you take a point, say over some finite extension in M of capital K, for finite extension capital K, the sheaf of automorphism is represented by a linear algebraic group. Okay, so this is the definition of a linear germ. Then there is an embedding of this germ into some the germ of SLN torsors, which is not a very interesting germ because of course you know that SLN torsors over fields are all trivial, but as a germ it is a nice object. And this is the correct analog of the embedding of an algebraic group into SLN. And putting those statements together, we can now make the dévissage in the right-hand side category and deduce some geometric dévissage on the left-hand side. So you really have to think about Mx, the germ Mx, as a replacement for the stabilizer H. Okay, and the first corollary, kind of corollary application we get from this point of view is what we called. So there is a classical Noname lemma for say finite algebraic groups, saying that for linear algebraic groups, if you embed a linear algebraic group H into SLN for one embedding, or for another, if you choose two embeddings of H into SLN on SLM, the quotients are stably birational. And here we get some version of the no-name lemma, which we call no-name and no rational point lemma, saying that two homogeneous spaces of SLN with isomorphic or equivalent associated gerbs are stably birational. So if this gerb is trivial, if it has a section of a little k, then you get two homogeneous spaces of SLN with a rational point. So in fact, this is a classical no-name lemma. But here we get birational isomorphism between variety which are not necessarily, we do not have in general rational points if the gerb is non-trivial. So it's a funny consequence. And except this funny consequence, we can now prove the main theorem 1. maybe I can switch. Okay. Equivalent, I mean equivalent, yeah. Yeah, I didn't write it down, but I mean equivalent. Okay, so to prove theorem 1, we define the notion of a good property of homogeneous spaces. So if P is a property of, say, of algebraic variety, so we say that P is a nice property of homogeneous spaces if for all such spaces the three following properties hold. So the first one is that P is a birational invariant. So if x and y are stably birational, then P of x is equivalent to P of y. So if you think about the Brauer-Manin obstruction to the Hasse principle or to weak approximation, it is okay. If you consider a morphism of homogeneous spaces with a section, then the property of for x implies the property for y. And again, if you think about local global principles and so on, this is quite obvious that it is satisfied for these properties. And the third property is that it is the one that is, of course, these two properties are satisfied for the, these two facts are satisfied for local global principles for any varieties. But the third one is specific to homogeneous spaces. So if you have a surjective map of homogeneous spaces with fibers which are nice homogeneous spaces, which means homogeneous spaces of a simply connected group with a semi-simple stabilizer, then you want to have that P of, you want to have a vibration situation. You want that if the base satisfies the property, then the total space satisfies it. So P of y implies P of x. So this is what we will call a good property, and you can check using, it's here that you use Borovoy statement or Kneser, Harder, Chernusov. It's here, it's hidden here in the fact that the fibers are nice, have nice arithmetic properties. It's hidden in this third property. And the theorem says that nice properties can be reduced to homogeneous space of SLN with finite stabilizers. So this is a general version of theorem 1. So theorem 3, nice properties for such a P P is satisfied for all homogeneous spaces if and only if P is satisfied for homogeneous spaces of SLN with finite stabilizer. So you can try to apply this reduction to other properties. And Harpaz and Wittenberg managed to prove that a variant of the conjecture of Colliot-Helen about zero cycle also satisfied these three properties here. So that's why they could reduce their general theorem to the case of homogeneous spaces of SLN with finite stabilizers. For instance, the property, if you are over a good field of cohomological dimension 2, the property that the homogeneous space has a rational point is also a good property. So you can think of other properties that can be reduced to the case of finite stabilizer. And so in the 5 minutes remaining, I will explain just the. I will give a picture. I will give a picture of the steps of the reduction from the general homogeneous space to a very special homogeneous space, which is a picture that is a summary of the proof of theorem 3. So you start with your homogeneous space X. So I will do some abuse of notation. So I will write the group acting on X as G over X. Of course, this is just a geometrical of an image over K bar, right? But just to keep in mind that X has an action of G with stabilizer H bar defined over K bar, okay? This is just a homogeneous space of G with geometric stabilizer H bar. This is the notation. What we construct, taking a nice resolution of the algebraic group G, we can construct, say for instance, you consider a flask resolution as defined by Colliot-Helen. So this is a linear algebraic group which is, the derived subgroup is simply connected. So it's a little nicer than the original one. And you take the same homogeneous space but with an action of a bigger group, okay? So the stabilizer is a little bigger, but the finite part of H bar is the same, okay? Then you embed here, for this step, you embed the gerb of mx0 in a gerb of torsors, as we mentioned before, okay? So you can, using the equivalence of category that I mentioned, using this embedding, you can construct a homogeneous space M1 of some group G1, which is just G0 times SLN, the same n as here. And you can, with the same stabilizer, and here this is just a projection, right? And you can check that since there is a section here, there is also a section here. So it will be, you could deduce the property for x0 from that of x1 using property 2, I think, yes. Okay, so this has a section, so it's fine. Then you mod out by, you take the maximal torus quotient of G0, you mod out by the derived subgroup. You do the same on x1, so you get some x2. And you can check that the fibers are simply connected group quotiented by a semi-simple group. So which is nice in viewing the third property. We could deduce the property for x1 from that of x2. And now the stabilizer has changed. It is an extension of a finite group by a torus, which is simpler than a general linear algebraic group. Okay, and then you go on. You go up to some x3 with a section. And now the group will be taking some nice resolution of the torus T. You can replace it by the quasi-trivial torus. So here you can put a quasi-trivial torus times SLN. And the stabilizer now is still finite by torus here. And what is nice about this group is it's a special and rational group, which means its Galois cohomology is trivial over any extension, and it is a rational variety. So it's very nice for geometric and arithmetic applications. Then, using the Noname lemma that I mentioned before, you can replace it by another homogeneous space, or for some, you can get rid of the torus, okay? And the stabilizer is the same, so still finite by torus. And since they are stably birational, property 1 is fine for us. So this is, say, G4 maybe. Yes, G2, G3, G4. And it's almost over. Well, then there is okay, I don't have the time to explain. So you go until X7. The idea is to replace this torus here. Keep in mind that this torus is not defined over K. We want to replace it by something which is essentially a quasi-trivial torus. We want to replace it by a quasi-trivial torus, and in the end we will only keep the finite part. To replace it by a quasi-trivial torus, we have a nice result, nice resolution of torus by quasi-trivial torus, but they are over K, of the base field. Here we are not over the base field, and we only have, in some sense, a torus of a K bar with an action, not of the Galois group, but of, in some sense, an action of a germ on the torus. So we have to prove the existence of nice resolution of torus with an action of a germ to make everything Galois equivariant. This is what we are doing now. So we do this using this nice resolution, and in the end we get some X7, which is a homogeneous space of some SL and R. And the stabilizer now is finite. And all the steps involved here satisfy property 1, 2, or 3. So the property, so in the end you get that P of X7 implies P of X naught, which is P of X. And so it proves the reduction statement. And I stop here. Thank you.
If you take a homogeneous space such that the stabilizer is not finite, but the group of components is finite and supersolvable in the sense of Harpaz Wittenberg, does it imply that Brauer-Manin obstruction is the only one?
It's not completely clear because what we can prove in the end is that the finite group here, of course, this is related to the group of component, the finite group of component of the initial stabilizer. It is this one. It is an extension of this one by a finite abelian group. So probably it's not super solvable in general, or we don't know how to prove it, but it's not far from being super solvable. So that's all I can say right now.
Other questions? Yeah, go ahead. Yeah, you. Oh my God, can you pass it?
So looking at reductive groups over p-adic or local function fields, one can use the theory of affine buildings to detect non-emptiness of certain Deligny-Lustig varieties and also the dimension of like non-emptiness of the varieties. Have you ever used this in your work, or do you think it's a valuable approach?
So I didn't use this kind of method. Maybe it's useful.
Okay.
Maybe it could be used. I don't know. Sorry, I have
Thanks.
no better answer to give you. We can discuss this later if you want.
Any other questions? Okay, if not, let's thank the speaker again.